So when it's just the carbons, it's fairly straightforward to identify the chain. You just want to count how many carbons we have in a row for our longest one. And then from there, we're going to use the different prefixes in order to give it its name, right? So 1 is meth, 2 is eth, prop, bute, and so on. So in this one, we have 1, 2, 3, 4, 5, 6, 7. And since there's 7 carbons, then we should be looking at heptane, right? Now we know it's an ane because this is what we call a saturated compound. That means that there's no double bonds. So if we go back and we actually attached all of those hydrogens, you can see that every single open spot for that carbon is filled with a hydrogen. And so that's how we know it's an ane. Now I'm going to take those back off. And so if we go through and we add in a double bond, we want to think about how that now changes our name, right? So instead of being just our heptane, we should have that changed. Now, is this big enough, or do you guys need me to make it bigger on the screen?
It's fine to me.
All right, perfect. So when we're looking at this one, right, we've added a double bond, and so it needs to change something. Now, our number of carbons hasn't changed. It's still 7. So we're still going to start with that hept part. So it's still HEPT, but now instead of being an A-N-E ending, we need to end it with an E-N-E. So now this is going to become heptene because it has that double bond present. Now, a lot of times, when your double bonds either on the carbon 1 or carbon 7, right? Basically, when it's at the beginning part, they don't list the number for it because it's assumed that if the number is not there, that you would know it should be on the first one. But you can list it if you want. You can list it either in the front like that, 1 heptene, or you can list it as hept 1 ene. Right? Oh, sorry, I forgot the 1. Right? Both of those will work. Right? What I recommend is put your number right before your suffix because it's not always in front of that compound when you have more than one suffix. We're not going to worry about more than one suffix for our class, but that is something that you can get into a little bit in the future. We're going to draw another one. We're going to look at that compound over there. So let's get rid of our heptene. And so now we want to go through and we want to name this compound. Okay. We're going to start that off first with just its basic shape. And then from there, I'll add on some functional groups and we'll go over that part. Once you have your answer, go ahead and put it into the chat and we can go through those names. Oh, well, we're just going to leave the carbons on for now. Just know that when you get your exam, we will actually be doing your line drawings. And so there wouldn't be a carbon here at each one of those joints. So you just want to make sure that you remember that. So Ziad is right. This is going to be a cyclo, and this is going to be pentane because there are 5 carbons. So 1, 2, 3, 4, 5.
You said when you're doing the test, we're just drawing the skeleton. We would just draw a hex.
So when you get it for your test, you guys are just going to be getting the skeleton. So you would get something that
it just has 5 corners.
Mm-hmm. Let me see if I can get it to come out now. I'll show you an example of one, and then we can do that. But either way, so this is going to be
on there, or we would just assume that it's saturated.
So you would get actual line drawings, and so I'm going to show you an example of one, and we can go over that part as well. But for right now, this is cyclopentane because it's got 5. One way to think about this is if you look at your compounds, if it's a ring, the shape that it gets kind of gives you an idea about what name. So this one looks like a pentagon, which is where it gets pentane from. If it looks like a hexagon, because it's got 6 carbons, then it would be hexane. Okay? Now, our line drawings for pentane look something like this. So this is what you get when I export them for you guys' exam, right? And so you just have to remember that on each of these junctions is a carbon. So we'd have 1, 2, 3, 4, 5. So instead of being a cyclo, because it's not a ring, then this is how it gets its name pentane. It's all single bonds, straight chain, and so that's where we get the name from. Now, when we think about numbering, I'm going to give you an example of one here. This is still pentane, but now we have a different arrangement here. So this is with our bromos. So just like with our kind of like our metal complexes, as we're going through, we want to start to identify your pieces. So the first piece we're going to start with is our pentane. Okay? That's our base. To there, I want to show, okay, we have one bromo group connected here, one bromo group connected here. And so I want to showcase that part. So I need to add that in. Now, if I have 2 bromos, then that becomes dibromo. Or actually, I don't need that space there. Dibromo, pentane. But now I have to indicate where they are. It's not enough just to tell me that you have 2 bromines, because those bromines could be anywhere on there. And so now we have to go through and we have to number our carbons. So if we start from the left-hand side, if this one over here becomes carbon 1, then we would be carbon 1, 2, 3, 4, and 5. So that would be that we would say, oh, there's a bromo on carbon 3, there's a bromo on carbon 4, and it's all part of our pentane chain. Now, the hard part about that is that when we have this one is we don't want to be using the higher values. So if we can come up with a numbering system that will give us a lower value, we would rather do that. And that's where our options for numbering kind of vary. So we could have numbered it from the left and gotten the value that you, or the name that I wrote in the chat, or we can have it go from the right-hand side. And if we do go from the right-hand side, then this becomes carbon 1 over here on the right. This next one becomes carbon 2, which has a bromine attached. Carbon 3 has a bromine attached. And then 4 and 5 don't have anything on it. So we always want to choose the numbering system that's going to get us the smallest values. So we're going to choose this one because it's going to give us the bromines added onto the closer carbon. Right? So you're always going to start numbering from the closest side. You want to try to basically choose your lowest numbers there. Does anyone have any questions about that, how I chose that side? Then let's do a very similar example. This is going to be with iodo. And then let me pull this over here. Hold on one second. Oh. Sorry, that's not letting me do it. There we go. That's what's the problem. There you go. Can you guys see the this new compound with the iodines?
Yes.
Okay. Go ahead and write out the name for that one. And then in the meantime, I'm going to fix my Marvin sketch. So once you guys have your answer, go ahead and put it up in the chat so we can see what we're getting. So you're right, there are two iodines, right? We still have the pentane backbone, but you have to be thinking about how many different numberings you need to stay.
How many different what?
How many different numbers you need to say.
You have to say 2 twice?
Because you have to indicate that both of the iodines are on that same carbon. Right? If you only give
Wouldn't the dye mean that though?
the di means that there's two of them. It doesn't necessarily mean that both of them are on the same one. In the same way that dibromo doesn't mean that both of those bromines are on the same. So,
Right, I get it, but I'm saying because I put the 2 there, then I'm saying that there's 2 iodides on 2, like because I didn't specify another number.
yeah, I get what you're saying, but you actually have to put the 2,2-diiodo.
2, okay.
Yeah.
All right.
All right, we're going to keep this going. And so we're going to throw out another compound. This one's going to be our foray into a different type of functional group. And so this one has a lot going on. And so what I would want you to do first is go through and identify your different carbon or your longest carbon chain. So we'll see who can come up with the longest chain of carbons for this compound here. So when you think you have the longest carbon chain, then go ahead and put it into your chat.
Oh, you don't want the whole name? You said just the
I don't
chain?
need we're just going to do the chain part. So we're going to do it in sections. So we're just finding the longest chain first. So how many carbons do you see there for your longest one? Right. Now, can you guys see my mouse? Is it visible enough?
Yeah.
Okay. So if we're looking, right, we want to think about all of your different carbons. So at each one of these junctions, there's a carbon. So we have a 1, 2, 3, 4, 5, 6, 7 of them, right? If we had gone and counted down, right, 1, 2, 3, 4, that wouldn't be our longest one. If we started over here and counted 1, 2, 3, 4, 5, 6, that wouldn't be our longest one either. So Naoki is right. It should be 7 for our longest chain. Now from there, there's different functional groups. So I want you to go ahead and identify what additions or what substituents we're going to add on to that heptane. So when you see one, you can go ahead and put it out there. Okay? And we're going to slowly compile a list so that way our name will include all of them. Right? So we're going to look at which one or what different groups we need to account for. All right, so let's go through this. So right now, we have a couple of different options of what we need to be looking for, right? So we decided that this one here was going to be our long chain. So that's 1, 2, 3, 4, 5, 6, 7. And so we've started to identify points. So we have a ketone. That's very true. Our ketone is going to be this one in red here with oxygen. Now, how do we know that that's a ketone and not something like a carboxylic acid or an aldehyde?
Attached to carbon groups, functional groups.
Because when we look
R's.
at it, the carbon that's attached at the bottom, it's connected to another carbon and then another carbon. So it's not connected to a hydrogen, which would mean it would be an aldehyde, and it's not connected to an OH, which would make it a carboxylic acid. So that's how we know that it's a ketone. Right? Then you guys are right that we do have a chlorine, and we have another chlorine over here. So we have chlorine that we need to account for. Is there another group that we need to look at? We do have a methyl, very good, because that's not part of our chain. So we're going to need to account for that as well. And so there's one other functional that we need to account for.
The bromine.
The bromine, right? And so we still have this bromine here. Right? So we have a lot of parts that we're going to need to put into this name. And so now we need to first decide what way to number. So as we're going through and numbering, we have two options. We could number from the left to the right or the right to the left. So I'm going to go from the left to the right. I'm going to number that in blue. So 1, 2, 3, 4, 5. That's a terrible looking 5, 6, 7. And then I'm going to number back the other way in green. So that would be 1, 2, 3, 4, 5, 6, 7. Now, those are the only two ways we can number this, right? Because we're on that longest chain, and so we always are going to use the longest chain when we're going through our naming. We can either number it from left to right or from right to left. And so what we wanted to look at is where does our numbers kind of start from, right? When we're going through and we're numbering them, we want to look at what's going to give us our lowest values. So right now we have a chlorine that starts either on 2 or 6, and we have another one on 3 or 5. Right? And then we have our ketone that starts on 2 or 6, and then the methyl that's on 3 or 5. So when we have those choices, right, we have to be able to decide which one we're going to start with. Now, what I'll tell you is that there is a list of priorities for your functional groups, so you can determine which ones kind of go first. Right? Your double bond gets a priority, and all of these ones that contain oxygens get a priority over things like the methyls, the chloros, the bromos. Right? So they're in their own kind of priority sections. Now for our class, I wouldn't give you this exact problem because I wouldn't make you choose between them. But you do need to know that you need to go with the lowest numbers for your substituents. Right? So in this case, we're actually going to number from left to right instead of from right to left, because when we came down to this choice right here between the chlorine getting the 2 and the ketone getting the 2, we need to give the 2 to the ketone. Okay? So we're going to start with the blue one. So I'm going to go ahead and erase the green numbers. And so now we have our numbered compounds. Now this is what I would recommend if when you take your quiz or your exam, is draw out your line structure so that way you can physically number them if it's becoming a problem for you. And so we know that we're going to start with heptane. We don't have any double bonds or triple bonds on there, so we can leave that as it is. We're going to add on that ketone. So how do we show that we have a ketone? What do we use for that part?
Own.
Own, right? So it ends in an O-N-E. So right now, this one right there, that's telling us that we have a chain of 7 and there's a ketone on number 2. Right? So that's our beginning part.
It's heptanone, not heptone.
Heptanone, yeah, because we're, well, hold on. I have to double check. And so that's what we're going to start with. And now from there, I want you to think about what order we should label the other substituents. Yeah, it should be heptanone, right? So we're just basically removing the E, we're putting in the O and E.
Is that for all functional groups? You keep the AN in it? Or
I believe for all of the like alcohol and things like that, yes.
okay.
Right, so that's why it's pentanol instead of just
Pentanol.
pentanol.
I got
Yeah.
you.
So from here, between our bromo, our chloros, and our methos, who's going to go first for the naming? How do we decide which one of those gets listed first in the naming process?
Alphabetically.
Alphabetically, right? So when we come down to naming, we're going to go and do it alphabetically once we have all these substituents. So out of the ones that we have, who is going first? Right? So we took care of the ketone. That one we're not worried about. Who's going to go next? What are we going to start with? Is it going to be the bromine, the chlorine, or the methyl? So either everyone really knows this or no one really does. And so that's making me worried, right? So it should be our bromine. Our bromine is going to come first. And what number is our bromine? It's number 4, right? So we should have it start with 4-bromo because we're starting with the bromine. And then after bromine, who comes next? So the chlorine's coming next. Now, can we just say chloral, or do we need to put something in front of it because there's 2 of them? You're right, Stephen. It needs to be dichloral, right? So after we have those, then we're going to move on to our methyl. So when we have all those numbers in there, you kind of get this big, long complex, just as it's written. We get 4-bromo, 5,6-dichloral, 3-methyl, heptane, 2-one, right? So it's kind of a whole big mouthful in there, right? And so what you'll notice with these is because they're all one compound and one name, you kind of don't want spaces between them. You're going to use those dashes, and that's how you can connect them all between each other. So this is one of those more complex structures where I might have you go through and list what functional groups are present, and then at the very end have you guys name it, right? And so this could be something that you would see. We wouldn't have to worry about both of them having the same number and how you choose between them, but you would have to know that we should start on the left because it was the lower number than if we had started on the right. So let's say that if I just got rid of this chlorine over here, so if I didn't have this one here, we should know that we needed to number from the left to the right because that ketone should have started at 2 instead of the chlorine starting at 3. Right? So you do still want to know that part.
Is there a reason why you don't put a hyphen between the last group and like your final, like your carbon chain name? Like, you know how you...
Oh, I see. Instead of just saying methyl dash heptane or whatever.
Because you're only putting the dashes to separate the numbers?
So basically you're using the dashes to separate your substituents. And then once you get with the heptane, you no longer need to do it because they don't really get the... I guess there's not really a clear reason why. It's just the way that it kind of is now when I'm saying it out loud, because you should know that methyl and chloral kind of aren't going to be all bridged into one. You would
Right.
know that the number should go with the one afterwards. But I
Right.
think that is just the convention of how they make it so it
Yeah,
looks
I was
clean.
also saying because like you see here, like you're separating the hyphens to separate numbers, and since you're not putting the 2 in front of heptane, you're putting it in front of own. I'm like
Yeah.
saying that's why it's just fluid because there's no the hyphens are only there to signify
When you have the number and who the
carbon.
number is
Yeah,
going with.
exactly.
Yeah, I could see that. I'm not 100% clear about why. I'll look into that and see if there's an explanation that's given.
All right.
Right. We'll look at another compound here. Let me just go ahead and. So go ahead and name this one. Let me get my face out of the way. And so, oh gosh, all right. Let me put this on this side. There we go. Let's go through and let's go ahead and name that one there. I re-put in that name so that way you can see it all written out, right? And so now we're going to look at this methyl one. I'm going to pull this up here. And so look at your longest chain first and start from there as you're looking at your names. Now, you want to be careful about finding your longest carbon chain. You don't want to just stop at where the alcohol is, right? And so think about really how far can that chain go? So when we're looking at this one, sometimes how people refer to this is they would tell me that this is a butane chain. That you go 1, 2, 3, 4 carbons long. And then to that last carbon, you add in an alcohol and 2 methyl groups. But our base shouldn't be butane. Our base should be pentane because we should really go 1, 2, 3, 4, and we should include one of those methyl groups to make us 5 carbons long. So instead of that carbon or that alcohol being attached to the number 1 carbon, it's really attached to the number 2 carbon. So we have pentane 2-all, and then we have a methyl group attached to it. So it should be 2-methyl pentane 2-all.
Isn't that a aldehyde?
This is not an aldehyde. Aldehydes have to be a double bond.
Oh, so this is just that alcohol. Got you.
This is just an alcohol. Does anyone have any questions on that part? Now, is there a type of structure that you guys would want to see? Like, is there a functional group that you guys are struggling with naming or something like that that you would want to see? Or do you just want to see a complex one, kind of like what we did with that, the heptane? So I'll wait to hear what you guys say so we can think about what options you guys want to see. All right. Any other options? Otherwise, we can definitely do that. Okay. So I'm going to go ahead and build out a structure. And we're going to put a couple different groupings in there. All right. So we're starting out so far. I'm going to build a little bit more on this. So we have an ending there. So I need good. So let's go ahead and go through and name this compound there, right? As you start to get your answers, go ahead and put them in, right? And we'll start to edit those as we go, unless we just manage to nail it out of the park on the first one. That's totally fine. And then at the very end, we can do a check. Now, some of you guys are talking about R groups, right? Now, in your, when you guys see your formula sheets or like the functional groups, they have a tendency to write your R and then they have it attached to different things. So if I do an example down here. So if we change this over to an oxygen, yeah. The reason why they're using that R is that R is supposed to stand for these different carbon chains. Now, you could have that carbon chain be a long one or a short one. It doesn't matter as long as it's a carbon. You can stand for it with R and R prime. R prime just means that it's another type, so that means that they don't have to match. If both of them were R, then it would imply that they matched. And so you could just have that as a stand-in. So that R could mean that there's 3 or 4 carbons in the chain connected there. It doesn't really matter. It just means that there's more structure on that side. If it wasn't a carbon, then that's why they would have that H, which is telling you that it has to be the hydrogen. So in this case, that makes it that has to be an aldehyde, right? Because it's that carbon, it's connected to some carbons on this side and then an H over here. So I'm going to turn on the numbering for us so that way you guys can see if you numbered it correctly. Never mind, it's not working out that way. So if we're thinking about our carbon chain, our long one, right, we should have 1, 2, 3, 4, 5, 6, 7, 8. And then we have 2 choices. We can go down for 9 and 10, or we can go up for 9, 10, and 11. Right? So we should be going with our 11, right? So it should be the not deca, it should be the undeca, right? Because now it's going with 11. Now for you guys' quiz in your exam, I really won't be going past 10, right? So make that simpler, we just take out that 10. And so that's going to be our longest chain, is it's going to be, instead of going with our ethyl group down here, we want to be going up top. Now, Sorry about that. From here, we have that longest chain. There's a couple of different functional groups that we need to be aware of. We have a double bond here, which is our ene. We have a bromine, a chlorine. We also have a methyl and an ethyl. So we have a lot of different options there. So now that you know where your longest chain is in your groups, then think about your numbering and think about which one should go first. Zia, you're almost right, but you're missing a section on your for your substituents. So go back and look at your substituents. You have a mistake in there. Oh, sorry. Let me move this one over. So we're going to wait and see what other people think as you guys weigh in. So we're still waiting to see if anyone else has thoughts about what the name of their compound should be. So once you have it, it doesn't, even if you don't know how to do everything, put out what you think it is, and we can go from there and try correct on that part. Okay. If no one puts out a guess, it's hard for me to figure out where you guys are at or where you might be getting stuck at. You can also send me questions if you have questions. You can answer those as well. So this is making me a little bit worried that no one else has a thought about what this structure should be. So right now, what I want you guys to do is just go ahead and type in where you're at, right? Let's see where we're at. So that way we can move from there. So I just need you to put in, even if it's not done, right? If all you know that is that you have a 10 chain carbon, then put that in. And so that way I can at least see where we're getting stuck at. So undeca would have been used when we had 11, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Or when we had the 11, so when there was one more out there, then it would have been 11 and would have been undeca, right? But because I generally don't make you guys memorize over 10, then I just took out that one carbon so that way we're down to 10, right? So right now we're having the carbon chain, so that's going to give us our deca, or decane would be our carbon chain of 10. And so moving from there, we have decane. And then Kaylee's right, it should end in ene. We know that there is going to be an ene on there, so we have that part. And so when we look for our ene, right, when we're doing our numberings, are we going to start from the left and go right, or from the right and go left? What do you guys think for our numbering? We're going from the right to the left because of where that double bond is. That double bond gets the priority over all of the other ones. And so we want that one to have its lower number. So this is going to give us 1, 2, 3. So this is going to be dec 3-ene. Right. Oh, sorry, let me put that out for everyone. All right. And then from there, we can build our next pieces. And so bromine does go right. So you guys were right about that. So it should be 8 bromo. And then from 8 bromo, what comes after bromo? Right, so we got 8 bromo in there. What's coming next in that list? Between our ethyl, our methyl, and our chloral, we should have our chloral. So that's coming in next. Very good. And then after that, what comes after chloral? Is it going to be our methyl group or our ethyl group? Ethyl. And so what number should that ethyl be? 4. Very good. And then what number is our methyl? 9. So when we type all of this out, we get 8 bromo, 7 chloral, 4 ethyl, 9 methyl, deca 3-ene. Like that. So for this program, Marvin Sketch is a free program, right? So if you wanted to get it, let's say that you were going to go on into more organic chemistry and you want to be able to draw molecules, that is something that you could get, right? The other part that's nice about it is once you draw your structure, I can have it generate the name, right? So if you want to do some practice ones, you can draw your own structures and then you can have it name your structure. And it will go through and it will do that, right? So right now it's gone through and it's done it for this first one. It also gives us this additional information where it's going through and it's actually talking about the arrangements. But we're not going to worry about the arrangements. That's something that we'll do at a later one. So now that we've gotten rid of this big one, what I'm going to do is let's look at this next one down here, this one over here on the left. Now, what kind of functional group do we see in this one? It's a functional group we haven't seen before, or at least we haven't talked about it today yet. What functional groups do we have there? So butane, right, the 4-carbon chain, that is different, but that's not the unique functional group for this one. So if we're looking at that, we definitely have a methyl group, so that's one of the options. We also have this double bonded O and alcohol next to it, and that's going to be our carboxylic acid. So that is right, that's what we're looking for. So we have a carboxylic acid right here. So sometimes carboxylic acids get a little bit confused because people include them as a ketone and an alcohol. And so you do want to be aware that when they're both connected to the same carbon, then they become something different, right? They become a carboxylic acid. Now, carboxylic acid is really important in biochemistry. They're like a very mild, weak acid. And so they get used in a lot of different biochemistry reactions. So when we name our carboxylic acid, we basically go through our longest chain, so 4, and then we're going to use that oic acid on that part. So this is butanoic acid, and the carbon here is always carbon 1. So our methyl group is going to be attached to what carbon? So what carbon is that methyl group attached to? So if we're counting, if our carbon in the carboxylic acid is 1, then this should be 1, 2, 3. And so we're connected for our methyl coming off the 3rd carbon. Right? So we have to start from the right because we're starting with the carboxylic acid. So 1, 2, 3. So we're looking for 3 methyl. And then we have a butane with an oic acid. And so that would be our name for that one. So sometimes I think with carboxylic acids, the hardest part is identifying that you have one instead of misidentifying it as a ketone and an alcohol. And then the second part is just remembering to start with that carbon. That one's going to be our number 1.
So it's oic for carboxylic acids?
Yeah, so this one's going to be an oic acid.
Okay.
Yep. And so you do want to have the acid part there. It is a part of their name, right? So make sure that you have that as well. Now we're going to look at this one over here as well. This almost said the name right there. This second compound. Right? And so go ahead and name that second compound as well. So what functional group do we have in this second compound? Very good. It's going to be an alcohol. It's a 3-carbon chain alcohol, so that is going to be propanol. And we're going to start the numbering from the side closest to a functional group, since it's there. Right? So isopropanol is an alcohol that looks very similar to that. Right? Isopropanol is just its common name, as opposed to its more formal name. So that's why it doesn't have any numbers in it. Right? Now, does anyone have any questions about how we name that? Then for the extra credit of the day, if we were to react these two things together, right, we react them together, does anyone know the type of compound we would make? So if we mix the carboxylic acid with an alcohol, and let's say that we add in some acid and a high heat, right? So we're going to encourage that reaction to get produced. We're going to make water, but something else as well. So we're looking for this reaction, carboxylic acid and alcohol. So what happens is that this oxygen is going to go and pick up a hydrogen, and it's eventually going to leave with this hydrogen as well. So we're going to get a shift that happens here. And so this carbon, that alcohol, is basically going to come and add on onto this one. And we're going to get something that looks like this. Now, what kind of compound or functional group is this one? It does have a ketone in it, but there's something else. Right? So when we have a ketone and we have this oxygen connected right next to it, so it's kind of like our carboxylic acid, except it's got a big old chain of carbon groups after it instead of the H. This is what we call an ester. Now, esters are a really interesting compound. They have a very sweet smell for a lot of different ones. And so I always like to talk about esters a little bit because they are a unique they have some interesting compound chemistry that comes with them. Right? And so esters generally have a smell in the same way that metal complexes have colors associated with them. A lot of esters are sweet smelling. And so they get engaged a lot if you weren't into like perfumes, right? Things like that. They look at different kinds of ester compounds, right, to get those scents.
Why is that that single O not an ether though? Isn't an ether an O connected to 2 carbons?
So you are close, right? The difference though is that it's got this O that's double bonded to that carbon as well, and that's what prevents it from being an ether. So an ether and an ester are very similar to each other. Okay. But the ether, we would now basically not have this. So and this is an ether.
2 hydrogens on each of those opposite C's.
Exactly. So those C's can't be attached to an O as well, right? Because otherwise we would have it classified as both an ether and an ester. And so you only have it as one. And so once this becomes that double bond there, in the same way that an aldehyde is not really counted as a ketone, or a carboxylic acid is not really counted as a ketone, it's that similar concept that this is a little bit more specific.
Because that O minus that connected with the propanol, that's a part of the ether. I mean ester, not like that's the COO in the
exactly. This is the COO part as compared to the COC.
I got you.
Okay, and so when we have our esters, the way that you kind of name them is you have to look at which side comes from your carboxylic acid and which side comes from your alcohol. And so I just wanted to show you guys that today so that way you guys can kind of see what that comes from. So if you take that from that O with the side that has the double bonded O, all of this is going to be what comes from the carboxylic acid. This section comes from the alcohol. So when we go through and we start to name these, the way that we name them is we name the alcohol side first. So that's propyl, right? Because it's the 3 propanes. And then we name on this side the carboxylic acid. So this was butanoic acid or methylbutanoic acid. So this becomes methyl. And then instead of ending it with ic, it becomes this O8. So this becomes propyl from the alcohol, and then 3-methyl-butanoate. And that's how you name your esters. Now, the part to remember for your esters is that I want you to be able to identify which part goes with your carboxylic acid group and which part goes with your alcohol group. Right? It's a big part in the naming part, but it's also just a good thing to know when you guys get into the mechanism. Then it really will show how you attach the different parts to them. But I just wanted to make sure that you understood how to divide it. So take that O, or take both O's, and those should go together, and those are going to be your carboxylic side. The other side is going to be your alcohol side. And so that's kind of how you guys can come up with the naming parts. Now, chapter 22, I feel like it's pretty straightforward. It's kind of like atmospheric chemistry, in like a lot of it is more about applying the concepts to like real life situations. And so what I would recommend for your like preparing for the quiz for chapter 22 is look at the homework, right? Your homework questions will kind of mirror what kind of questions we're looking at. So a lot of it is concepts from Chem 120 just applied into a new setting. So it might be like finding the oxidation numbers for your hydrides, right? So being able to identify hydrogen's oxidation number when it's combined with lithium compared to that when it's combined with like carbon per se. Right? Some of it might be that if we were to do like wanted to make ammonia using nitrogen, what kind of yields will you be looking at? Things like that, right? So if you can do your homework for chapter 22, then I would say that you should be fine, right, for your quiz. We have about 5 to 10 minutes left. So if there's a specific topic that you guys want to see, we can do that. Or what I would really recommend doing is, if you haven't done the reaction prediction worksheet, it's a good thing to start to practice. I've made the answer key and I've uploaded that as well. And so it's just a good thing, so that way you can practice looking at your pieces, understanding your functional groups, and then thinking about how they're connected. Now, all of the stuff that involves an oxygen group, they all have like a series of oxidation and reductions that kind of connect them together. So like a ketone is your middle. If we reduce that, we can get alcohol. So, sorry, everything basically starts with alcohols. If we oxidize them, we can make ketones or aldehydes. And if we oxidize an aldehyde, we can make that a carboxylic acid. We can then react your carboxylic acid with more alcohols to make your esters. And so there's like a series of family reactions there. And so you just want to have a concept about how they're associated with each other. I won't make you guys identify the different reactants involved, but I might tell you, well, if we were to oxidize an alcohol, what would we make? The other part is when we talk about like primary, secondary, and tertiary. If I turn this into an alcohol, is that going to be a primary alcohol, a secondary alcohol, or a tertiary alcohol? What do you guys think?
So if you oxidize it?
No, so just as this is written, is this a primary, a secondary, or a tertiary? This one's going to be a primary because it's at the end. Very good, right? Now, if I add another carbon here, this has now become a secondary alcohol, because this carbon that the alcohol is attached to is now connected to 2 other carbons, so it's going to give it second. If we attach another one here, this is now a tertiary alcohol. And that alcohol, or that carbon's connected to 3 different carbons. Now, can we take a tertiary alcohol and turn it into a ketone by making that a double bond? Is that possible?
Not with 3 other carbons attached to it.
Right? So if it's a tertiary one, we can't make it a ketone, right? But if it's only a secondary one, we can make it a ketone, right? So this is what happens when we oxidize it. And if it was a primary alcohol like this, when we oxidize it, what did it now turn into? So if we had a primary alcohol and we turn that into a double bond, it's not an alkene because the double bond's not between the carbons, but it would be connected to an aldehyde because this carbon is connected to a hydrogen.
I didn't notice the hydrogen. I was like, what? It has to be attached to them.
Right? And so that's the tricky part about alcohols. Depending on what degree they are, tells you what they can kind of oxidize into. So a primary one can go into an aldehyde, and a secondary one can go into a ketone, and then the tertiary one doesn't do anything when you oxidize it because it can't fit all of those bonds. The other part that I wanted to go through is that if we have a double bond here and we add in our bromines, your bromines kind of split and attach one to each side. Yeah, you get something that looks like this. Oh, and we need to make the double bond go away. Okay. If you start off with a alkyne, so if we start off with a triple bond here, we would have to do that twice in order to get all of it to go away. If you only do it once, we can add in the bromines here. But we'd get a double bond that remains. And so we could do it another time. We could add in another bromine to each side. And then we would have it saturated. Right? So every time that you add in the halogens or hydrogen or the HX, you're going to slowly start to take away one of those double bonds and replace it one to each side. Now, there is a special relationship to that in that if this is a double bond here, when you add in your compounds, the side that is more substituted, so the one that's connected to more things, it's the one that gets the halogen. So if we had an option between giving this one the H or the bromine, let's say that we're adding hydrobromic acid to it, this interior one is going to get the bromine, the exterior one's going to get the H, right? And so that's how you can kind of make that choice between it. So I covered that inside of your like alkene and alkyne reactions in here. So if you're confused about that, look in the answer key and they kind of walk you through that part as well. Reaction prediction is not going to be a huge part for your exam or your quiz, but it is something that you want to be at least a little bit familiar with. I think it makes it easier to understand how the functional groups kind of fit together. So I would encourage that. I think that helps with that. Where that might be looking at is you should know your alkene reactions. So what happens when you add H2 to an alkene or Br2 and the HBr. Alkynes kind of fit right into that part. And then for your alcohols, really what I'm looking at is if you take an alcohol and you oxidize it, what can it turn into? So whether that's primary, secondary, or tertiary. If you take an aldehyde and you oxidize it, what does that turn into? And then what's the opposite of oxidizing something? What's the reverse reaction for something that oxidizes? Reduce. So anything that you oxidize one way to make it into an aldehyde or a carboxylic acid, if we reduce it, we should be able to turn those back into either. So a carboxylic acid can get reduced into an aldehyde, and then the aldehyde can get reduced into an alcohol. Right? So there's that forward and backwards between them.
Another way of looking at oxidation is that just adding the capability of adding bonds.
So
Like
it's not just the capability of adding bonds, but it's more like you're electron deficient, right? So you're adding an H plus, and so a lot of your things that have lone pairs will start to interact with that H plus, and so that's why your bonds kind of shift around a little bit.
well, but it's like it wouldn't technically be electron deficient though, because you're losing hydrogen to be able to oxidize it, correct?
Yeah, and so you're putting in something that's electron deficient, and so things with electrons will interact with it.
Because
So you're making
because you lose the H, it becomes electron deficient.
So your system is kind of becoming electron deficient. You're encouraging things with extra electrons to go out and make bonds. So sometimes they will leave because they've made water, things like that. Sometimes that they will go out and they will connect with other things to make those bonds. So that's kind of like the difference between those. But in a lot of cases, when we're building things, a lot of it's through oxidation.
But like if you already have an O double bonded, like you're going to know that oxidation is not going to occur. Like the only thing that can happen is reduction in this basic case that we're working with.
Yeah, that oxygen can't get any lower.
Like it can only turn into an OH. Like it's not going to turn into a triple bonded O.
So you're not going to turn into a triple bond. You can only go into an OH, which would be the opposite side.
Okay.
Yeah. So if you wanted to look at an example of a reduction, so that would be like if we had something that looks like this. This is well, let me make this into something first. Right? So this right now is a ketone, right? So if we were to reduce this, right? So if we added in like a reducing agent, what this is going to do is instead of being a ketone anymore, it's going to turn into an alcohol group. Right? And so that's how we can take our ketone and we would turn it into an alcohol. And more specifically, we turned it into a secondary alcohol as we went through that process. And if you had something like a carboxylic acid, so I need to make this an O and this an OH. Right? For a carboxylic acid, when we reduce it, the first thing that leaves is going to be this OH. It kind of gets picked up and goes away. And so this becomes a hydrogen. And so what would this now become? What kind of functional group is that ending now?
Aldehyde.
An aldehyde. And so then if we continue on this, if we reduce this further, this will become an alcohol. So when we reduce, we kind of go up the chain. We go from ketones to alcohols. So anything that's a double bonded O will move on to becoming an alcohol. If you have an alcohol, you will become kind of water and you disappear, right? That's kind of like how that process goes for reducing.
So is the process of reduction, is that either that you're adding a diatomic halogen or hydrogen, or you're using hydrolysis, you're doing a hydration?
So neither of those are reducing, right? It's more that you're adding in like a reducing agent. And so we haven't really talked about them because to know exactly which compound becomes a little bit more complicated. In the same way that if you were making a galvanic cell, you would use certain metals in order to reduce some things, but not everything.
Right.
Your processes go through a similar situation. So you only use some reagents which will oxidize like weakly, or you will use some that oxidize very strongly, depending on which direction you're going. When you're going on the reducing side, that's the same thing. You could use a strong reducing agent, or you can use a weaker one, depending on where you want them to stop.
So you're saying that
we're not going to worry about that.
Some functional groups, like maybe a ketone would be able to go through hydration with a water to like get reduced, but like an aldehyde might not be able to do that with water. Like it might
so like some of them, like an aldehyde's more reactive than a ketone. So an aldehyde is easier to reduce down than a ketone is.
So like you could use water. You could do a hydration reaction potentially for aldehyde, but like maybe not for ketone.
I don't remember if there's just one for aldehyde. Normally with the aldehydes, I think we use, no, actually, I think it's water and then you use high heat, right? But yeah, that's not going to be something that we're going to worry about for our class, about the conditions for all of it. But that's something you get into with organic chemistry.
All right.
Mm-hmm. All right. Well, so that pretty much wraps it up for today, right? I would definitely recommend